Alright, let's see if we can figure out how to go the other way. We found a v versus t from an x versus t and an a versus t from a v versus t. That involves finding slopes of lines or curves, and we've talked a little bit about that. This is called differential calculus, and as I told you before, it's kind of cool to be able to realize that you're doing calculus. Turns out we're going to go the other way. We can start with an a versus t graph and find a v versus t graph, and then from that a v versus t graph, find an x versus t graph. This will involve finding areas under lines. This is actually called integral calculus, so more calculus. We're going to simplify it down to finding areas of rectangles and triangles or trapezoids. Let's start with the v versus t graph and see how we can find an x versus t. Here is the v versus t graph. It shows an increasing velocity, in other words, an acceleration. Since the slope of this line is constant, as we've learned before, the acceleration of this object is constant as well. Let's look at one of our kinematic equations. This is the one that relates x final to x initial, v initial, and v final, and time. It does not have acceleration in it. So here's the equation. Look at that right term. The second term is really the equation for the area of a trapezoid. The two bases are the VI and the VFs. The height is t, if you kind of look at it sideways. If you look at the graph, this would either be the area of a triangle, where one base would be 0, or the area of a rectangle, where the bases are equal, or a regular trapezoid, just like we said. Let's see how this all is going to help us. So here's a graph of the velocity versus time again. We need to make a data table and fill it out as we go. There's going to be 3 columns. The table is going to consist of time, delta x, and x final. The t column is just the time. The delta x column is the area under the curve between the adjacent times, and the xf is the sum of the total distances. So we start out with our table, filled in with the first line being at 0, 0, 0. We always start at t equals 0 and delta x equals 0 unless I tell you otherwise, which means your x final position for time equals 0 will also be 0 unless I tell you otherwise. The first delta x will be the area under the curve between 0 and 1 second. That's that blue triangle that just floated in. You know how to find the area of a triangle. It's 1/2 the base, which is 1 second, times the height, which is 2 meters per second. Multiplying that all out is 1 meter. So the delta x for the 1 second interval is going to be 1 meter. We would add 1 meter to the previous 0 to give 1 meter as well. This is what our new chart would look like. After 1 second, my object is moved 1 additional meter, which means it's going to be finally at the x equals 1 meter position. Now I want to find the area between 1 and 2 seconds. This is also a trapezoid or a triangle with a square on the top. This will also easy calculate, giving delta x of 3. So the x final would be 1 plus 3 equals 4. Here's the red triangle flying in. Notice the area of the triangle is 1. The area of the square underneath it is 2. 2 and 1 is 3, giving the 3. Filling in the table, we find that after 2 seconds, my delta x was 3 meters. Add that to the previous 1, giving me a final location of 4. I'm going to continue. I can find the area between 2 and 3 seconds. This is another trapezoid or another triangle on top of a couple of squares. Again, an easy area. The delta x is 5, so my final x would be 4, the previous 4 plus the new 5, giving 9 meters. These yellow area flags in. I can see the 2 rectangles have an area of 4. The one triangle has an area of 5, so there's my 5. Adding this to my table, I find that my delta x for 3 seconds is 5 meters, giving me a total distance of 4 plus 5, or 9 meters. You see how this all works out. It's not terribly hard, and there is some consistency to it. It's just calculating areas and triangles and adding them together. If I finish the remaining 2 areas, I get the table as shown above. After 4 seconds, I would be at 16 meters. After 5 seconds, I would be at 25 meters. This allows us to calculate the x final as a function of time. If we were to graph this x versus t that we obtained in the last slide, this is the graph we get. Look at its shape. It is a parabola just like we've been working with before. It is curvy, so that means there is an acceleration. We made this graph from a velocity graph, which also indicated a positive acceleration. The math to do this, as shown previously, can be a little bit difficult. You gotta have to keep track of things, but it's certainly not impossible. It is the areas of triangles or squares which sometimes get combined into trapezoids. So remember the chart below. To go from x to v, you take the slope. To go from v to a, you again take the slope. To go from a to v, you find the area under the curve. To go from v to x, you again find the area under that new curve. Areas don't have to be positive. If for some reason my graph goes below the horizontal axis, well, that means my area would be negative. Negative velocities, for example, mean that I'm moving backwards. A negative acceleration would mean I'm having a negative velocity. That's it for the reverse. Given one of the three graphs, either an x versus t, a v versus t, or an a versus t, you should be able to determine, estimate, or calculate the other two, either by taking slopes or areas or whatever combination you need to do.